Welcome to Chapter 3 of Class 9 Science, Atoms and Molecules. In this fascinating chapter, we'll explore the fundamental building blocks of matter and understand how everything in our universe is composed of tiny particles called atoms. The quest to understand what matter is made of dates back thousands of years to ancient Indian and Greek philosophers who wondered how small matter could be divided. Maharishi Kanad in India proposed the concept of Parmanu, the smallest indivisible particles, while Democritus in Greece called them atoms, meaning uncuttable. Today, we'll trace this journey from philosophical ideas to modern scientific understanding of atoms and molecules. Let's begin with the ancient theories of matter. Around 500 BC, both Indian and Greek philosophers independently arrived at similar conclusions about the nature of matter. In India, Maharishi Kanad proposed that matter could be divided into the smallest possible particles called Parmanu, which could not be divided further. Pakuta Katayama elaborated on this idea, suggesting that these particles exist in combined forms, with different combinations creating different types of matter. Meanwhile, in Greece, Democritus and Leucippus proposed that matter consists of indivisible particles called atoms. While the Indian approach was more philosophical and spiritual, the Greek approach was more materialistic. Both traditions laid the groundwork for our modern understanding of atomic structure. Now let's move to the foundations of modern chemistry with the laws of chemical combination. In the late 18th century, Antoine Lavoisier, known as the father of modern chemistry, established these laws through careful experimentation. The law of conservation of mass states that mass can neither be created nor destroyed in a chemical reaction. In Activity 3.1, when we mix two solutions and weigh them before and after the reaction, we find the total mass remains unchanged. The law of constant proportions states that in a chemical substance, elements are always present in definite proportions by mass. For example, water always contains hydrogen and oxygen in a 1:8 mass ratio, no matter where it comes from or who prepares it. These laws provided the experimental foundation for atomic theory. Let's explore John Dalton's atomic theory, which revolutionized chemistry in 1808. Dalton, born in a poor weaver's family in England, became a teacher at age 12 and eventually a school principal. He combined philosophical ideas with experimental evidence to propose his atomic theory. The key postulates were: all matter is made of very tiny particles called atoms. Atoms are indivisible and cannot be created or destroyed. Atoms of a given element are identical in mass and properties. Atoms of different elements have different masses and properties. Atoms combine in small whole number ratios to form compounds, and the relative number and kinds of atoms are constant in a compound. This theory beautifully explained both the conservation of mass and constant proportions laws. Now let's understand what atoms really are. Think of atoms as the fundamental building blocks of matter, similar to how bricks are the fundamental units of buildings. Atoms are incredibly small. A hydrogen atom is about 10 to the power of -10 meters in size. More than millions of atoms stacked together would make a layer barely as thick as a sheet of paper. While we can't see individual atoms with our eyes, modern technology like electron microscopes allows us to image them. Everything you see around you, this screen, the air, your hands, is all made of atoms. The amazing diversity of materials comes from different combinations and arrangements of just about 100 different types of atoms. Let's learn about atomic symbols and atomic mass. Initially, Dalton used pictorial symbols for elements, but this system was complex. Berzelius suggested using letters from element names, which became our modern system. Each element has a symbol with the first letter capitalized and second letter lowercase. For atomic mass, we use a relative scale where carbon-12 is exactly 12 atomic mass units. One atomic mass unit is defined as 1/12 the mass of a carbon-12 atom. This allows us to compare masses of different atoms easily. For example, hydrogen has atomic mass 1 U, carbon has 12 U, oxygen has 16 U, and sodium has 23 U. These values help us understand how elements combine to form compounds. Now let's explore molecules, groups of atoms that behave as single units. A molecule is the smallest particle of an element or compound that can exist independently and shows all the properties of that substance. Molecules can be of elements, containing the same type of atoms, like oxygen molecule O2, or of compounds, containing different types of atoms, like water molecule H2O. Molecular mass is the sum of atomic masses of all atoms in a molecule. For example, water H2O has molecular mass 18 U, carbon dioxide CO2 has 44 U, and ammonia NH3 has 17 U. Understanding molecules helps us comprehend how atoms combine and why compounds have specific properties. Let's discuss ions and ionic compounds. Ions or atoms are groups of atoms that carry a positive or negative charge. They form when atoms gain or lose electrons. Positive ions are called cations, like sodium ion Na+, and negative ions are called anions, like chloride ion Cl. When sodium and chlorine react, sodium loses an electron to become Na+, chlorine gains that electron to become Cl, and these oppositely charged ions attract each other to form sodium chloride NaCl. Polyatomic ions are groups of atoms that carry a net charge, like ammonium NH4+, hydroxide OH, and sulfate SO42. Ionic compounds typically have high melting points, are soluble in water, and conduct electricity when dissolved or molten. Now let's learn how to write chemical formulas. The step-by-step process involves writing symbols of elements, writing their valencies below, crossing over the valencies, writing the formula with subscripts, and reducing to the simplest ratio. For example, for calcium oxide, calcium Ca has valency 2, oxygen O has valency 2, crossover gives Ca2O2, which simplifies to Sao. For compounds with polyatomic ions, we use parentheses when needed, like calcium hydroxide CaO2. Understanding chemical formulas is crucial because they tell us exactly which elements and how many atoms of each are present in a compound. This allows us to predict properties and behavior of substances. Finally, let's review everything we've learned in this chapter. We traced the journey from ancient philosophical ideas about atoms to modern scientific understanding. We learned about the laws of chemical combination that provided experimental evidence for atomic theory. Dalton's atomic theory, while not completely correct by modern standards, was revolutionary for its time and explained many chemical phenomena. We distinguished between atoms, molecules, and ions, and learned how to represent compounds using chemical formulas. Most importantly, we now understand that the incredible diversity of materials in our world arises from different combinations of just about 100 types of atoms. This fundamental knowledge forms the basis for all of chemistry and helps us understand the world at its most basic level.